Welcome to today's webinar. Today our topic is System Assessment and Certification of HIPPS, Turbines, and Other Bespoke Systems. My name is Chris O'Brien, and I'm going to lead us through this webinar. A little bit about myself. I graduated from Villanova University with a Bachelor's in Mechanical Engineering. I started my career as an application engineer with Moore Products Company. I was there in multiple roles. During that time, I received 5 patents, including a patent for the industry's first safety-rated pressure transmitter. After that, I was at C&D Technologies, where I was Vice President of Power Systems. At C&D, we made large-scale DC backup systems. In 2005, I joined Exida, and I'm a partner who works extensively with our clients in functional safety applications of 61511, 61508, ISO 26262, as well as the machinery standards. I'm co-author of the Final Elements book, and since 2019, I've been CEO of exida.com LLC, and hopefully my 35 years of experience might bring some insight today. So today we're going to take a look at bespoke systems and talk about the application of 61511 to them. How do we pick the correct standard? How do we effectively implement an assessment project? Avoiding errors and rework, and finally, we'll have some time for questions and answers at the end. So the functional safety standard market and adoption continues to grow. The standards have gained considerable traction in many countries and industries. In some geographies, they're actually even a requirement to show that equipment such as turbines comply with 61511 before you can get approval to operate. So organizations need to be able to show that those deployed systems are properly managing risks. Safety professionals working in those plants or evaluating those systems need to be able to efficiently execute projects where they may not be experts in all technologies. So these standards that provide communication across industries and applications really do help there. As a little bit of an example or study, we could take a look at the different verification and validation methods that are available or commonly used and see how much of a safety lifecycle do they cover. So this chart is it's a little bit of an eye chart, but it's a pretty good study of if you had a subsea HIPPS system, depending on what information is provided or complete, how well have you covered the requirements in the assessment. So in the vertical column, or vertically, we've got different techniques such as SIL verification, a final element compliance report, all the way down until like an integrated final element assembly, safety reliability analysis, and application check at the bottom. And then across the top, we have everything. These are the different things that are necessary to check. So are the requirements documented? Do the requirements cover all the applications? Are the design specifications correct? All the way over to, is it installed properly, and is operation and maintenance correct? Now you don't have to, a user doesn't have to necessarily require certification or something from the supplier, but the less information that comes with the system, the more the burden is put on the user of the equipment to collect and show themselves it's there. So this is a kind of an interesting study. So we kind of propose kind of steps of let's determine the right standard, and if it is 61511, how would we implement that assessment? And then finally, let's look at some common mistakes and rework we've seen done, and maybe ways to mitigate it. So first question is, which standard to use? So the standard's got to, 1, be right for the application, 2, meet regulatory requirements, and 3, in our opinion, be well understood and accepted by industry. So why? So the first one, you should use a standard that's appropriate to the application you're doing. That seems pretty obvious, but kind of the benefit of that is there's a lot of knowledge built into application standards. So they're taking many years of expertise, and that's being captured. Now sometimes they might be prescriptive, and maybe there's an alternate way to do it, and the functional safety standards certainly let equivalent methods be done. So the standard should also address any regulatory requirements. So as I mentioned, many countries will require IEC 61511 for things such as turbine or fired equipment before they allow them to go online. But there also could be other standards, such in the US, there's going to be NFPA standards that are going to cover burners. There's going to be subsea standards in the North Sea or in the Gulf of Mexico. So those are important to have on the list as well. And they should be widely accepted. So the importance of the acceptance is that the more people and more segments of an industry that are aware of a standard and understand it, the better the communication across organizations. So that's really an important feature, we think. So many people say, well, why do we need another standard? We've got lots of regulations, we've got lots of standards. Well, the functional safety ones really are focused on, one, providing a safer working environment for people and literally saving lives. It also helps protect investment in plant and equipment, ensure the operations are running, and that is, it's to save money. And it demonstrates compliance with regulatory requirements, and that is, it helps avoid fines and getting operating permits. There's lots of things that influence the adoption of SIL standards. So certainly we can start with national regulatory requirements. Then if we go around clockwise, there can be competitive offerings. Different people may have different things that are certified. That helps them in the market. There are application standards. More and more application standards are calling out for a functional safety assessment. And there can be customers' expectations. So with these bespoke systems, there's more and more focus on what can be documented or provided by the supplier to show that they are designed and implemented properly. And if we go back to that kind of stoplight chart, more evidence and verification information comes with the system. So how could a standard help? It documents industry best practices, as we said, provides consistency across organizations. And in this case, those organizations could be the OEMs, the integrator, the ultimate user, and EPCs. You're also less likely to miss a step if you're following a defined step-by-step method. And common or known mistakes are explicitly addressed in these standards. So when we're looking at things going into the process industries, there are two main standards we kind of run into, IEC 61508 and IEC 61511. Now, if you're a supplier of devices or equipment, such as transmitters or logic solvers or valves, that is going to be IEC 61508. So that standard is the standard for suppliers. If you're buying a system in the process industry specifically, you've got an option for IEC 61511. So when would we decide that it should be a 508 cert or a 511 cert? Well, here's a couple of things that help guide that decision. 61511 is going to be more applicable or appropriate if, like, the languages are limited to limited variability language or fixed programming language. It's a system that's tailored or unique by project. It's site-specific, and it includes most or all of the safety lifecycle. So if you're having a turbine, that turbine really isn't going to be assessed to 61508 because so much of that management of the system and assessing how it's done is going to be specific to the siting, what plant, what application, what are the things around it, and the supplier of the turbine isn't going to have all the operation information and maintenance information to do it. On 61508, that certainly would apply to, say, a pressure transmitter or speed sensors or the controller going into that turbine control, but then they're then used. There are some things to consider, though. If that application, even if it's going to be dedicated to a plant, includes full variability software or embedded software or hardware, that is going to have to be evaluated, at least the device or the part of it in that system, to IEC 61508. If you've got FPGAs or ASICs, which are field programmable gate arrays, things that are complex semiconductor devices that are configured to do the job, that also is going to make it fall under 61508. And potentially, if you've got a standardized solution, say, a HIPPS system that you think you're going to build 100 of, and they're going to be the same, then it might be appropriate to get a 61508 certificate for it. So 508 is going to be very good at covering a standard design, but it's also always required if you are going to be deep into like an embedded development environment. 61511 is very good for looking at bespoke systems for a plant. If we take a look at kind of these systems by application, the largest application is ESD, emergency shutdown system. So that's a very general category. So that's the typical, hey, if I've got a chemical plant and a safety system, it kind of falls into that category. Fire and gas are exactly the fire and gas detection systems. That's the second largest at 32%. And the final three, turbo machinery, burner management systems, and high integrity pressure protection systems, or HIPPS, they're each about 10%. So that kind of, when we're looking at these systems, gives a bit of a breakdown. So we go back to our question about which standards are applicable. To determine that or make that full judgment, you're really going to need to have an understanding of local and national regulations, be aware of any specific device standards. So especially in Europe, there's many different device standards. So, you might have to have something for the system, but the devices might have to meet specific standards as well. And you'll have to know if there are any application standards, such as NFPA, you want to consider. So there is a bit of work that is required to go into this, but if you're in a plant or there, you're probably pretty familiar with it just because you've had to do it to operate. But we do see lots of questions, and this kind of gives a little bit of an insight, and we can kind of give the answer. So should turbo machinery be covered by IEC 6111 or the machinery directive? And the answer is yes. So for process-related hazards, such as collection of unexploded gas in the duct system and explosion, that is a 61511 question. Loss of control over speed of a turbine, that is a 61511 question. Burning, hazard caused by moving parts and machine type things, that is definitely a machinery directive issue. Next is we're seeing more and more of this. Does the machinery directive require my device be certified by a notified body? So there are requirements in the machinery directive that logic solvers and other things be assessed to ISO 13849 by a notified body. So there are some ways that does happen. Another common one is, hey, if I implement my burner management system to NFPA, will I meet 61511 and vice versa? And the answer is typically mostly meet, but you've got to always check the requirements of each standard you're going for. And even if there's high overlap, anything that's incremental, you need to add on to it. So it's not an absolute yes. So if we look at those 5 different kind of categories of systems or applications and take a look at the systems, that's kind of useful. So for emergency shutdown systems, they are used in pretty much every industry and in every geographical location. They have very high variability in their design. And they have unique features. So they range from everything from simple interlocks all the way up to very complex protective functions. So, this is a case where if you're required to show compliance to functional safety, IEC 61511 is very much going to be the standard because it is designed to look at each system uniquely through the whole life cycle. Fire and gas systems are used extensively in oil and gas, power generation, and the chemical industry. They have high variability because they're very much a function of not only the gas or the combustible materials, but also the layout of the plant. And they do have unique features, especially in siting and sensor layout. They really have a big impact of the effectiveness of the system and require special expertise. Turbo machinery are used extensively in oil and gas and power generation, and a bit in chemical and pulp and paper and cogen sites. They have moderate variability. They're often a supplier is going to have, a turbine supplier is going to have a list of standard safety instrumented functions they're going to use, and that's a good starting point. But there are unique features, so you really need to understand the application and the siting of that turbine. And for example, if they're in island mode or grid connected, that has a significant impact on risk targeting. Another commonly seen application is burner management systems. They're used in many industries and applications. They have moderate to low variability. Again, there are standards that call out many of the protective functions, but there are unique features. while many burners are similar, or many boilers or many fired equipment is similar, there's an awful lot of very unique custom designed fired equipment, and that needs special review. The other thing we see a lot is, since a piece of fired equipment is often delivered as a subsystem from a supplier, we see lots of breakdown in communications or incomplete communication between the user and the supplier of the equipment. So that is an area we would recommend focusing on. And then HIPPS systems are used extensively in oil and gas and power generation. They have moderate to low variability in that, usually there's one function, protection against high pressure. But one thing to remember and consider is that there's often a lot of design-specific things for the valves, depending on, is this coming off like an oil or gas field where there's going to be different composition of chemicals and corrosives in the gas or liquid. And again, quite a few of these are used for subsea, and they have their own set of complexity to consider. So let's take a look and talk about IEC 61511 and benefits of that. So if it is determined that a 511 certificate or assessment is needed, either to make sure things are properly covered or that it is a requirement before the plant's allowed to operate, some good things about 61511, or strengths about 511, it is a comprehensive standard, and it provides very good guidance that can be applied throughout all the phases of a project. Multiple techniques are available. So for different things such as sill targeting, you are allowed to pick different techniques. So that allows companies to align what they're doing with what's required by the standard with what their practices in the plants are. And it's performance-based. So it facilitates aligning the effort for reducing risk with the actual risk. Let's walk through a general functional safety life cycle. So typically we have hazard identification, risk analysis and sill selection, creating safety requirements, verifying the design, implementing the design, and then sustaining. So with the hazard analysis, we want to know what can go wrong, and typical techniques for process hazard analysis would be a HAZOP. We want to do a risk assessment, and that's really how bad could this be, and layer of protection is often used. We're going to write requirements to document what needs to be done, and we're going to verify that system and show how reliable it is. And then we need to know how to keep it safe once it's been implemented. Now, different standards have life cycles. So IEC 61511 is a full life cycle that could be applied to bespoke systems. And really all functional safety standards have a life cycle that are some variation, but typically they all include analysis, realization, and operation. Before industry-specific standards came out, such as 61511, this standard would be used when something wasn't available that was tailored to the industry. 61511 has the same things, analysis, realization, and operation, but it's written much more from a plant operational perspective, so the terminology and the methods referred to are going to be very good for these bespoke systems that are going into the process industry. One thing we're going to talk about a lot, or you're going to see, is safety integrity level, and that term is used three ways. It is definitely used to establish risk reduction. That's often the most common concept, like, a SIL 3 loop provides more risk reduction than a SIL 1 safety function. That's true. So that's probably maybe the most broadly understood. It also sets probabilistic limits for hardware random failures, and it does establish engineering procedures to prevent against systematic errors. So the higher you go up, we see this more, you'll see this more in IEC 61508, where there's more distinction between the SIL levels and requirements. 61511 from a process perspective is pretty homogeneous, but there's a few cases where, and we'll cover one of them a little bit further, about proven in use, where you have to show more evidence. So let's talk about SIL targeting. So the purpose of that is to identify how much risk reduction is needed to attain a tolerable risk. And there are two broad categories. There's qualitative and quantitative. So a quantitative technique is going to give you a range. It's going to put you in a SIL band. You're going to get an answer of SIL 1, SIL 2, or SIL 3. You could get SIL 4, but 61511 is then going to require you to do 61508. Our quantitative methods, such as will give you a specific risk reduction target. And a key thing is you have to be consistent with the method or sets of methods to be used. So we say sets of methods because sometimes people will use a qualitative analysis to be sure they've identified every possible safety instrumented function. And once they're identified, they'll go back through and do a quantitative method to target them a little more precisely. So an example of a qualitative method is a hazard matrix. Basically, it's a matrix. It's a grid that shows severity against likelihood. And essentially, the higher the severity, the lower the frequency you can tolerate. And the practice there is we want to categorize the consequence, categorize the likelihood, and then select the target SIL from the matrix. And there you're going to get a SIL 1, 2, or 3. Another technique is called risk graph, and that is you use different parameters. So it's a qualitative method with a little bit of guidance as to when you consider avoidable or not, or some guidance built into the method. And it does, in a way, it even starts introducing the concept of independent protection layers like occupancy, ability to avoid, and the demand rate. So, so the first thing is, what is the consequence? And is it minor injury, fatality? That's going to pick which branch you're going on. And then you say, well, how frequently am I there? Is it possible to avoid? And how often does this occur? And by following that, you're going to get, maybe no SIL all the way up to a SIL 3. An example of a quantitative, and really the most common quantitative method, would be LOPA, and it's a way to analyze from an initiating event frequency through unique independent protection layers, and you put a quantitative number on the probability of failure of each layer. And if that layer fails, then the event propagates, and eventually you can get a consequence that occurs. So that, as you can just see by the different techniques, that takes a little bit more time than, say, a risk matrix, but it's going to provide a more refined target number. And just for an example, here's a pipe rupture example. And in LOPA, you don't take credit for the SIF. You kind of have initiating events, and you put numbers and probabilities on probability of failure on demand for each IPL, and you wind up with a calculated unmitigated event frequency. And then you can compare that based on the severity of the consequence with your tolerable frequency. Does it really matter what you use? It can. A common example is overspeed for a turbine. So you may have heard this, or often people say, oh, all overspeeds are SIL 3. Well, we've studied a lot of turbines, and I am not sure I've really actually done a quantitative analysis that showed it was SIL 3. But for a qualitative statement, SIL 3 means risk reduction of 100. Many of the analysis does show that it's a high SIL 2, so it might need a risk reduction of 600. I said qualitative SIL 3 of 1,000. Many quantitative will be a high SIL 2. So it does matter. It could lead to different results, which could lead to different redundancy requirements. Guidance would be, our general guidance would be, if you have a high risk scenario, a little bit digging in further and doing a quantitative analysis is often worth the effort. I like to advise against just taking a SIL target from a standard and basing it on industry practice, because it could be overspecified or underspecified. It's very unlikely to be exactly well calibrated for your site, because siting is such a key driver in consequence analysis. So if you're going to do an assessment to 61511, well, what does that mean? What do you kind of get when you make that decision? Well, you're going to need to use an appropriate SIL determination methodology. You're not going to be able to take, oh, I read, standard XYZ says this is SIL 2. You're going to need to use high integrity protective systems. You're going to need to separate physically and electrically your safety system from your basic process control system. You're going to need to do periodic proof testing according with procedures to do that. And you're going to need to document the proof test and the regularly scheduled reviews to show that that system is working properly. To show compliance with the standard, you're also going to need in the design, there's three kind of hurdles. SIL capability, meeting probability of failure requirements, and meeting architectural constraints. And it's only when all three of those things are met, you're showing compliance of the system with 61511. Each of those hurdles are for a different purpose. So SIL capability is really a strength against systematic failures. So this is in the equipment use. So that SIL capability shows that the supplier and manufacturer is making that equipment in such a way repeatedly that you're going to be able to trust what you get. And so how do you show that? You use certified equipment or you do a proven in use analysis. Probability of failure is a way to demonstrate strength against random failures in the system, which we know are going to exist, and you're going to do a PFD calculation. Architectural constraints are actually a protection against using unrealistic failure. So even if you said, my valve is fantastic, it never fails, there's going to be limits on what SIL level you can achieve without redundancy. And that's pretty important because that is something that is, the industry continues to get better, but there's different sources of data and some are just very optimistic. And the way you're going to show architectural constraints are either by a calculation of, say, failure fraction, using route 2H, and the required redundancy from those two paths. So to effectively implement getting a project assessed to 61511, we have a couple recommended steps. Kind of a benchmark study of what's there, and that's going to say, this is my system and process. So we've talked a bit right now just about verifying system design, but you also have to have that whole safety lifecycle in place, because we could under-design a system because we use low failure rates, or we could have a targeted system because our hazard analysis was incorrect. So a benchmark study looking at all the steps of the life cycle is a great place to start. And out of that will come some gaps, and you can implement a gap resolution plan. And often, really, the first step of that, if it doesn't exist, we recommend developing a project functional safety management plan, then going through system design, implementation, and then the operation and maintenance requirements. So in the benchmark study, what we focus on are safety management, safety lifecycle, risk assessment, SIL selection, really walk through the major phases of the safety lifecycle. And this helps group activities, often by different companies or groups responsible for them, but then also if there's gaps, then they can be attacked in a logical way. But you can see it kind of works from safety management all the way to through modifications and decommissioning to documentation. We've got really a safety case that we complete when we do this, and we've got summarized requirements, references, and we'll put in a compliance argument. And this is really helpful because you'll get detailed feedback as to what's missing and why, not just, oh, it doesn't comply, but, oh, you've got to do version control on your limit variability language you're using in your safety PLC. And, why do you do this? We can explain it and kind of point out where it's called out. Just use that as an example because that's one that we do run into somewhat frequently. Typical gaps: no structured process, no agreed upon or articulated tolerable risk, poor communication across organizations, missing or incomplete documentation, the use of non-SIL rated equipment without a proven in use analysis, not including all the components in the analysis or under the scope of what needs to be done, unrealistic modeling assumptions, or incorrectly modeled shared equipment. So those are not all of them, but some typical ones we see. So we really encourage establishing a process. Here's just a simple example. The more I do this, the simpler some of these things seem to get. It seems like, oh, it's basic project management. But all right, so if we're trying to meet a standard and there's all these different phases or requirements in it, and we're going to put a plant together and we're going to have a gas turbine and a steam turbine and other equipment, all right, do we know who's responsible for each phase, for each piece of equipment, and overall? So you can make a simple graphical chart mapping out equipment and who's doing what part and put names and responsibilities down there. Understand that safety systems need to be validated. So we've got to be able to require, collectively, exida and the implementers, what are the safety requirements? How are those decomposed down? So we're going to have requirements. We're going to have a conceptual design. That as a minimum is going to break between hardware design and software design. How are each of those things allocated and configured and integrated among themselves and then ultimately into a system? And do we have internal integrated testing, factory acceptance testing, site acceptance testing? And all these tests, we need a test plan and we need test records. So understanding that this really has to be a traceable from requirements to test results is helpful, and that those test results have to be, requirements have to be version controlled, test plans and results have to be version controlled. That's a big step forward in getting the right mindset to be generating the information throughout the project. So let's talk about typical ways to structure projects, documents. So having a functional safety management plan is very important. Detailed top-level requirements, such as competency and independence. We want it to address all phases of the life cycle. We want really clear descriptions of the handoffs between the phases and the groups working on the project. And we can have appendices that contain information that's going to be useful, such as definitions and SIL levels. From there could be group procedures, and they could be broken down between, say, EH&S and instrumentation and controls and maintenance, but something that covers each relevant phase, what are the inputs required and what are the outputs expected, often along with templates that show examples, and that really helps, again, improve communication and improve completeness. And then finally, a project plan to say, hey, here's how we're going to do it for this project. Here's how we're tracking the documents, who, what, when, where, how, with the appropriate sign-offs. And that all goes to when you build a big complex thing, how are you going to demonstrate at the end compliance? Because not everything's going to be inspectable at the end, or it's going to be a lot of rework or creating updating or creating documentation at the end and probably rerunning tests. So we recommend, there are 4 FSAs called out in the standard, but if we're looking to assess a system, we focus on FSA 1, which will be after the analysis phase, FSA 2, which I think a very effective place to do that is after the FAT, and then FSA 3 after the site acceptance testing. And you can do that, we know, what documents and steps should have happened, and you can even do a pre-assessment at the FSMP plan stage. At the end, you can get a type or a site certificate showing, kind of acknowledging that all things were done correctly and that site and that equipment is acceptable to run. Depending on what area in the world you're in, you're going to need these or not need these. Sometimes you'll just need an assessment report. Sometimes you'll need a certificate from a third party. And then finally, let's come back to avoiding mistakes and rework. So this pie chart is the classic one from the Health and Safety Executive out of the UK, showing the root cause of many failures of control systems. So we're going to touch briefly on errors in functional safety management and planning, errors in analysis, errors in realization, and errors in the operation and maintenance phase. So how do we avoid errors in functional safety management? I can't stress this enough, ensuring all parties clearly understand their roles and responsibilities. It seems so simple, but we're all so used to working with safety systems and designing plants and doing things that, our knowledge sometimes makes us think we have things covered. But, classic things, do the system integrators have a software specification and validation plan? So not just are they good at writing software, are they competent, but do they have a specification for the code that's version controlled? Did they implement it? And how did they validate it? Do they have version controlled FAT procedures and test plans for your specific system? Was the PLC configured per the OEM requirements per the given SIL level? And is the PLC code that's delivered on site exactly the same code that went through the FAT test? Now you can test, the benefit of the FAT is you're going to find things where they're easier to fix. You could do a full functional test on site, but that's often much easier to do before it's out of the factory. Hey, if it's not the same code, then you've got to do the gap between the two, and you've got to run whatever test on site you need to do to satisfy that verification step. And always, a pre-startup functional safety assessment. We'll often call that FSA3 right before the hazard's present, but that should be very comprehensive. We're not just checking code, we're checking to be sure all the previous steps of the safety lifecycle were done. Again, this is really, mapping those requirements through the functional safety management plan to group procedures to a project plan. And this should be available, we really recommend at the beginning of a project, and you're just completing it and filling out as you go, and then you're going to be able to drill into specific areas and solve those problems. Avoiding errors, some common errors in the analysis phase. Things that we see a lot are, one, assuming hazards are addressed by another party. I've seen, detailed safety analysis, HAZOPS reports and SIL verification, and in there's a clause like, it was assumed that pressure fluctuations that basically could blow out a piece of fired equipment or handled at the plant level. So there was an example of a kind of a packaged piece of fired equipment, and one of the main reasons you lose flame is loss of pressure too high or pressure too low coming in, and there was just a note in the documentation saying, we think that's handled outside our scope. That caused quite a bit of rework. Identifying all operating mode of the equipment, because the hazards are going to be different depending on the operating mode. Verifying all claimed IPLs. One case you could claim the turbine is so robust that if there's an overspeed, a blade can't go through the casing. However, there's often a generator attached to that turbine which is going to come apart if the turbine overspeeds. Be sure not to over or under claim BPCS credits. So whole topic for that, but that's something that's important to think about. And properly defining valve leakage requirements is another thing that is somewhat overlooked. Common errors in realization, not meeting SIL capability requirements, missing components or not including all components in the analysis, having some unrealistic modeling assumptions. We'll dig into all these a little bit more. Sharing components and having poor proof definitions. So 511 requires that all equipment be assessed to 61508 or justified based on proven in use, including any mechanical part that's such as a valve or you might have a hydraulically piloted poppet valve that's going to dump the hydraulic system. All those pieces are part of the safety system and need to be analyzed. There is an option for proven in use, but this places the burden on the equipment user. It really is difficult to collect statistically meaningful data unless you've got something in your plant and you're tracking hardware and software revision numbers. And essentially, it's going to require a formal functional safety assessment for SIL 3 for users, for a SIL 3 thing. So that basically says, okay, you've kind of got to do a 508 assessment yourself. So that puts a lot of burden on the users. Now, I always kind of group it, if you've got something with software in it, you really are going to have a hard time going down a proven use path because software changes are pretty frequent, relatively frequent. If you've got a large collection of mechanical devices or type A electronic devices and you've been periodically testing them and recording data, that's more reasonable. Or you could do a hybrid thing where we can help do a light review with suppliers for your specific application. Another thing, you could buy a SIL3 protective function, and I've seen this exactly where some SIL3 descriptions included only the safety PLC, some included only up through the trip block, which, making a, you can have 2 out of 3 sensors, transmitters coming in, you can have a 2 out of 3 trip block, but the final elements weren't included in that analysis. So it's not, a user could come to the wrong conclusion that everything is covered and it's not in there. Unrealistic modeling assumptions include claiming very high coverage for proof tests, such as 100% for valves, neglecting to account for mission time, and not accounting for beta or common cause where there's redundancy. And just a real simple example, to go, in this case, we've got a perfect proof test versus a 70% proof test for a final element, and that reduces the risk reduction, or putting a realistic proof test in there drops the risk reduction from 184 to 28. So you could get a 6x difference in risk reduction. So you really need to understand what you're claiming and why. I like to use this as an example of like a shared instrument example, because this is common in turbines. You're going to have a stop valve and a control valve, and it's really hard to fit more valves in there. So it's tempting to say, oh, I've got 1 out of 2 valves. Like in a specific scenario is, oh, if, this is going back to grid connected or not. Well, if I'm grid connected, I really can't ever overspeed because the grid limits it. But you're going to have load rejection. You're going to have different reasons where you're not grid connected. So we need to account for this modeling correctly. One way to do that, and it says, 61511 says you can't share equipment, with a caveat unless you properly model it and treat whatever is shared as safety critical. So in this case, you can have like independence all the way up to the solenoid controlling, or the hydraulic trip assembly, trip manifold could trip both valves. So you could show independence through the speed sensors, through the logic solver, through the hydraulics, all the way up to kind of the final control of the valve and the actuator itself. There is a way to do it, but in this case, if we took just the top rung here, we would be counting those valves as 1 out of 2, and if we look at that, we would get a risk reduction of that first bubble of 1,300. In reality, we have 1 out of 2 for every failure mode except when the valve causes the failure. So you can model that by saying, hey, I've got my total demand frequency on the top rung, and then I add to that the demand frequency is if the valve fails, if the control valve itself, control valve actuator fails. And I can add that in, and in that case, I have 1 out of 1 protection on the valving, and we can achieve a risk reduction of 678 in this example, and there's a white paper on our website about this. So there are cases where, if you took no credit for the shared valves, then that's way too conservative. If you assume that that control valve is always there to protect, then that's optimistic. So you want to model these things with a little more rigor, but they can be done. Then in system design, so what do we want to do? Select certified equipment when possible. Make provisions for automatic testing, because it's just going to be much easier in the operational phase. And that testing could be automatic diagnostics and automated proof testing if you can do it. And then consider, are things going to be rebuilt at different times? Because if they're rebuilt, for example, let's say there's an overhaul and every 6 years or 10 years you rebuild the valves, well, that mission time resets on the valves, even if you're going to do the safety system in 20 years. And then make sure you pick tools that have enough granularity to model that. And, Excellentia is an excellent tool. You're going to be able to put in all those variables that you need, mission time, proof test coverage, beta, and really get a realistic model of what you're going to achieve. In operation and maintenance, make sure you control access to the safety PLC, perform and document all the tests that are required. As things are identified, correct any systematic issues with components and or process, and perform FSA4s. That is called out to be periodically, validate those systems are running. We have, a process where we can do an FSA4 assessment, and we kind of track against 10 major areas of conformity and provide that feedback, really more for continuous improvement and benchmarking. So that's a lot of information. We're here to help. We kind of really offer everything from, we can help you with training. We have books and templates available. We can do those benchmark studies. We can help perform a CHAZOP. So many things like a HIPPS system or a turbine system that's going to be fairly repeatable, and the control system is pretty dedicated. CHAZOP may or may not be needed. We find in ESD systems, we're often asked to help. And the first thing is to understand, well, what is my system really doing? And doing that analysis to go and see, well, things might be shared you don't realize are shared. And the safety critical path might not be quite what you think it is. So CHAZOP is really helpful for doing that. We can provide advisory services and help make sure the project is set up and roles and responsibilities are defined. And then ultimately assessments and certification as needed. So with that, I'd like to thank you for your time and attention. And now we can switch and I'll take a look at any questions that have come in. Thank you.